All right, looks like maybe things are going to work. And so this is 127. And we're up to chapter 3, which is shellcode. So let's take a look at the slides, and it'll be mostly demonstrations, really. All right, so here's the topics. The protection rings in the processor and how system calls work is the main point of what we're doing here. And then we'll talk about how to make shellcode, how to assemble it, and then how to look inside it to see the assembly code inside there and follow the system calls and understand what you have to do to make real shellcode. The shellcode we're going to make at first is very inferior. So system calls are what actually does all the work in your machine. I mentioned earlier, you cannot your code that you run in userland, which is where everything you launch from the start button and a command prompt is, does not have the authority to touch the hardware. And yet everything you want to do involves using the hardware. So what you do is your userland code calls the kernel and asks the kernel to do things. And it does it with these system calls. So we're going to make shellcode. Shellcode is typically the point of an exploit. You want to run shellcode. The most common shellcode you want to open opens a network socket and then takes command line commands over the network socket. But the first shellcode we're going to do just exits. The next one's just going to spawn a shell just so we can see how it works. So system calls. Contact the kernel, and this is how you get input from the keyboard, put output on the screen, run a file, and anything else you want to do. This is because the protection rings in the processor. Your processor has a lot of instructions, but it also has 4 protection rings, although only 2 are used in modern operating systems. Ring 3 is userland, with less privileges, and many assembly language instructions are not usable in Ring 3. Ring 0 has the ability to use all the commands. And so if you want to do anything involving touching hardware, you will find you are not allowed to use that command in Ring 3. What you have to do is make a call to the kernel, and it will then do it on your behalf. So this is called protected kernel mode. So user applications cannot do something that would destroy the entire operating system. That's the point. If you make a mistake in your userland code, it will just crash your program, but the other programs in the operating system will continue running. So if you try to access kernel memory from userland, that's an access exception. You cannot directly access kernel memory. You have to make syscalls, which then launch processes in a kernel mode. C library that you use for almost everything, libc, when you're writing program, you use print and all the other commands. These are wrappers, and all they do is perform syscalls. So libc is just a way to make it easier for you to call functions, and they also mean that you can write programs in C, and the syscall, your C compiler will understand if it, or your library will be updated to match the call underneath. This is why you have several layers of indirection. Instead of directly calling the kernel, you call a C library function, which then calls the kernel. And that can withstand more changes. And we'll see that a lot as we go ahead and do exploits, that you do not usually jump directly to the kernel. You jump to a lookup table and then another lookup table onto the way to the kernel, because that way you can have an operating system update without recompiling your code, because it will change the contents of a lookup table, and so on. So the original syscall was int80. Int is an interrupt. It's a way to request a service in an asynchronous way, where the processor interrupts whatever it's doing and does something else. So you load the number in EAX. That always has to be there. That tells you which function you're running, and there may be other arguments, in which case it goes in the other registers, and then you execute int80. The CPU switches to kernel mode and performs a function based on what was in those arguments. So it's a syscall number is an integer in EAX, and these other registers are used for further arguments, and if you need more than 6, you can actually point to a structure, a data structure, although I've never used more than 2 or 3 of these for any of the simple things we're doing here. So I updated the demos to Debian 11, which was very small changes, and here we are with exit. So let me do this. Here's my Debian. I go to 127, and then chapter 3. All right, I've got a few things here. So I want exit. Okay. Oops, that's not right. Oh, e.c. All right. So here's about the simplest function you can possibly make. Let me fit it on the screen. All right. So you get the standard libraries, and then you make just a function that does nothing but call exit 0. So all it does is enter a C function and then exit to get back to the operating system. All right. Now we compile it with M32 and static. I don't remember why you need static, but it's static means it doesn't use shared libraries. Put the output in E and E.c, and this gives you an executable function E, and all it does is return back to the prompt without doing anything, but it does that without crashing. All right. So let's disassemble and find out how it works. So we've done this before, and we're going to need a little bit of room here. Okay. So we debug quietly E. All right. Now we disassemble main. Let me just check my log main. Then I follow exit. Yep. Okay. So I disassemble main. And here it is. This is the preamble, pushing the old base pointer on the stack and creating a new stack frame. Down here it calls some thunk thing. This is at the start of most programs. I'm not quite sure what it does. But anyway, down here we call exit. So it prepares things. This 0 is apparently the parameter 0 it's returning, and it calls exit. So main calls exit. So we can now look and see what exit does. Disassemble exit. All right. Disassemble exit calls run exit handlers. Okay. So let's see what that does. All right, this has the thunk stuff at the start and makes a stack frame, and then it jumps around a lot. What this is really doing is it's cleaning up everything that might need to be cleaned up when it's time to end your code. So it has all these conditions, and someplace in the lower middle, it's going to call another exit function. And I'm just looking at the calls. This is another way to do an int 80. Here it is calling free, which is cleaning up stuff. And here it is calling underscore exit. So that's what it does when it's done. Where's the syscall? We haven't been to the main syscall yet. There have been a few others. All these are just normal C functions. We will eventually hit a syscall. This calls exit, so let's quit out of that. And then disassemble underscore exit, which is what that function called. And this is where the syscall is. So it does all these other things, cleaning up all the various memory objects you might have created in your C program. And then when you're done, it puts 1 in EAX and calls int 80. That's the syscall. So, all right, that's all I wanted to show you. That's what really happens with exit. It just cleans up all this junk, and then it calls a syscall. All right. So there are 4 ways to do a syscall, by the way. Int 80 is the most common one. Sysenter is another way. This call GS segment register 10 is another way to do it. And there's also syscall at AMD 64. So all these will do the same thing. All right, so let's take a look at underscore exit. We did that, but let's take another look at it here. Notice there's actually 2 syscalls here. Here, remember this mess is also a syscall. That's just another way to write int x80. So first it calls syscall fc. ff is 255 and fc is 252. And gs is a segment register. So there's fs and gs. They point to the beginning of memory segments. So you can do calls by referring to relative addresses from these segment registers. It's another way to do the same thing. And I don't know why they do it that way. But that's why I had that. There are 4 different ways to do syscalls, and they all amount to the same thing. Now you can read those articles I've linked to in the lecture notes, and gets more clues why there are 4 different ways to do it, but they all do essentially the same thing. So what this does is it calls syscall 252 and then syscall 1. So sys 252 is called exit group, killing all threads in case your program is multi-threaded. So I mean, all that extra stuff is to just clean up all the mess you might have created in a C program. And the last one is exit, which kills the current calling thread. All right, so let's write shellcode for the exit syscall. Now the point of shellcode is you're going to use it in an attack, so you need it to be small and simple as possible. And this is because typically, as you're going to see a lot as we go forward, when you find a vulnerability, you get to inject code, but often you get to inject only a few bytes, like only 8 bytes or only 20 bytes. So you need something really small. So you typically, shellcode has no error handling, which makes it very fragile. So one frustration when you begin doing exploit development is your exploit will fail and you will have no idea why. Like if you make a remote shellcode, the most common one, that tries to make a network connection, if your network server is not available, it will just die and you won't know why. You'll think there's a bug in it, but it's not a bug. It was just unable to proceed because it hit an error condition and it has no ability to handle an error condition and print out an error message or anything. So the syscalls, there's a Linux syscall reference online you can get to and see them all, but exit is syscall 1, sysexit. And it has 2 arguments. EAX is 1, EBX is a return value, which we can use 0 for. So that's why all we had to do is set EAX to 1 and do a syscall to perform an exit. So this is the simplest code in assembly language to perform that. You define a main memory segment, you define a main object, then you have a text section, which is where the code goes, and there's going to be no other section. And in here you put 0 in EBX, 1 in EAX, and you call int 80. So that's what I've got here. Get out of here and exit.asm, I think. Yeah. Now that's assembly code, not C. You can write raw assembly code this way, but in order to compile it, you need an assembler. And Debian does not include an assembler by default, so you have to install NASM, just an assembler. And when you assemble it, you do assemble with the format of ELF32, so I'm making 32-bit object code, and you give it your input code, and it does not create executable code. It creates object code, which must then be run through GCC to link it. So again, you take that and link it with M32 and turn it into exit shellcode, and then you have executable exit shellcode. And when you run that, it just returns normally without an error message, so it's still just calling exit. So this is the first thing we're doing just to understand the structure of using the kernel, but we're not accomplishing anything yet. Now you can see the contents of object files and executable code with objdump. Objdump -d will disassemble any executable code and let you see the assembly code inside it. Exit shellcode. All right. So the various sections in here, these are all things we were looking at in the debugger earlier. And here's main. Main is our shellcode in this case. And see, here's the commands we put in. Put 0 in EBX, put 1 in EAX, and call int 80. And then there's a couple of bytes of what looks like just sort of senseless filler here. So notice it takes 5 bytes to put 0 in EBX, because we talked about this in the first lecture. This is a 32-bit 0 going into a 32-bit register, so it takes 4 bytes to store the 0, and BB is the code for move into EBX. And the same thing to put a 1 in EAX. So that's the raw bytes, the hexadecimal structure of your shellcode. Now you can test, once you've created shellcode, you create it in this form because you're going to actually inject it byte by byte in the hexadecimal into memory. Then one way to test it is to test it with C code. And so that's exit2.c is the one I wrote here. I had to change this a little bit from Debian 10. Oops. All right. Test exit2, okay. There we are. So what I did was I put it on the stack. So inside the function, I defined shellcode, and here I just put those bytes. These should look familiar. Same bytes we just saw. BB, 4 bytes of 0, B8 a 1, and some zeros, and this is the int 80. So you store those in a character, a string, and what this nonsense does is it defines a pointer to that as if it was a function and then executes it. So you can run code that's there. Now this will normally result in errors because you shouldn't be able to execute code on the stack. That's because of the buffer overflow attacks we're going to be running. So in order to do that, you have to compile it specially with -z exec stack. That tells you don't like it taking 5 bytes instead of 4 bytes. Let me answer that one. If you go back to here, here's the command, move 0 into EBX. The 0 takes 4 bytes. But the rest, this is the opcode to tell it to move into EBX. So the 34 bytes are for the immediate number, and you need at least one more byte to tell it what to do with it. So that's why move to EBX is BB, and move to EAX is B8. Okay? That's why everything that has an immediate constant is going to have at least 4 bytes for the constant and at least one more byte for the operation. Yep, good, good. I'm glad you're bringing up the questions. All right, so you got to use exec stack, and then it will run. So that's test exit 2 runs without crashing because I put it on the stock. Yeah, the command in this case is only 1 byte. That's right. Some commands are longer, but these commands are very simple. Command to move an immediate value into one of the registers. And there's only 4 registers you would use, A, B, C, and D. Well, I guess you might have ES, like I and such. Yep, that's right. These are very simple commands. x86 includes all sorts of complicated commands that are longer, but these are about the simplest commands you can get. So now we got running C code, which loads the shellcode into memory on the stack and runs it. Now we're going to use strace to see the system calls that it makes. And strace you also have to install on your machine. Test exit 2. Maybe I got to put in /. Should I spell it wrong? There, okay. Got to put in /. Okay. So what strace does is it shows you the system calls used to launch this program. And let me, there. So it calls execve, which we'll talk quite a bit more about later. This is how you create a new process by forking the current process. Then it does memory mapping. And notice these permissions on a memory region. It reserves a region of memory which is read or write, but not both at the same time. I guess that means read and write. Okay, read and write. And then it has another one, memory map, protected read, another memory map, deny write, and so on. These are creating all the memory regions that we've seen before. And when it's all done reserving all the memory and turning on protection for various levels, then it calls exit 0. So these are the system calls that reserve all the memory, load it into memory, run it, and then that calls exit 0. All right. So now let's talk about what's wrong with that shellcode. As you're going to see, the most common thing you do with shellcode is you there. All right. So if you did an obj dump and look at it, you'd see this. We saw this before. It's all full of null bytes. Now, most of the common situation for shellcode is you have some kind of data coming into a C string, like a username or a password or something, and you just put assembly code right in the string. But nulls terminate C strings. So if you put a null byte in a string, that terminates it, and nothing after that null byte will actually be sent to the computer and put in the memory. So you can't use shellcode that has all these null bytes in it. You have to avoid null bytes. And in fact, in real exploit scenarios, there are often a bunch of other bad characters you have to avoid. But you nearly always have to avoid null bytes. So you cannot use this kind of shellcode. You have to get rid of the null bytes, and that just means you have to rewrite your code carefully using different assembly language instructions that will compile into commands that don't have null bytes. So if you try to move the immediate number 0 into a register, That's no good. So what you do is you XOR a register with a register, and that will take whatever bits happen to be 1 and flip them. So this will result in putting a 0 in there, but it does not include a literal 32-bit 0 in the instruction. So that's a way to accomplish the same thing. This one, again, contains nulls because the 1 has 32 bits. But if you do this one, move 1 into AL, we talked about this the first time, AL is an 8-bit instruction. So you move 1 only into the lower 8 bits of A, and therefore you only store an 8-bit immediate number, which is not 0. So this is another way to accomplish the same thing. And so the old shellcode was this: move EBX0, move EAX1, and we changed that to XOR EBX, EBX, and move AL1, and then int 80. And that creates exit2 shellcode, which works the same way. And if you look at what's inside there, we can do it with obj dump. So I made, if I cat exit2 shellcode, did I call it .asm? Exit2.asm. Okay, let's take a look at exit2.asm. All right, there it is, with an XOR and a move AL. And if I do an obj dump, let's run the exit2 shellcode. Okay, it exits, and if I do an obj dump on it, there we go. All right, I see all the modules, and here's main. And notice now the shellcode is much shorter, and it no longer contains any zeros. This is only 2 bytes. To XOR EBX with EBX is just 2 bytes. And to move 1 into AL, here's the 1, and this is the command to move that into AL. So it's not to avoid recognizable patterns. The point is to avoid nulls, because you're going to be injecting into a string, and nulls have special meaning. This, by the way, is a highly troubling limitation of C, that null bytes terminate strings. In Pascal, strings start with a number, which is the length of the string, and the next number of bytes are in there, so you can use null bytes. Unfortunately, the C convention is that null bytes terminate strings, and that's going to turn out to create a lot of problems. And as I mentioned, all the memory exploits that we're doing here are all pretty much caused by the language C, which does some strange things which are hard to understand and confuse programmers. So here's our new shellcode. And so you can, all right, that's what you do. Now, these shellcodes do nothing but open a command prompt, a terminal, which you already had anyway, so you don't actually accomplish much of anything. So let's do a little bit more. If exit just stops the program, and that's not really anything special, what we'd rather do is open a shell that lets the person who injected this code now enter more commands. So here's what to make shellcode, you write high-level code, you compile it, then you disassemble it and analyze it, and then you have to clean up the assembly to get rid of those null bytes, and then create shellcode. So you go back and forth. All right, now to create a new process in Linux, which is what you want to do, I want to make code that will create a new process and then accept commands from the user. Fork and execve are ways to do it. We're going to use exactve. That will replace the currently running process with a new process. You can also create a new one without stopping the original one by using fork and execve together, but that's more difficult, so we're just going to use execve. Now, you can read about execve in the man page of every Linux distribution. It'll tell you how it works. It's in the Unix standard library, and it executes the program pointed to by the file name, and that causes the current program to stop and be replaced by this new program. It's got this weird system of parameters. So here's what you have to do it. The first parameter is you create an array with 2 pointers in it, and the first one points to a string which has the command you want to execute, which is bin sh, which will just open a shell, and the second one points to something like environment variables or something, and that can be null. But you have to feed in the string here, and then a pointer to an array of pointers that points back to the string again, and then the null. So the 3 parameters are very strange and redundant. The second one would be logically all you need. Why is it so important to avoid dynamic linking? I don't remember why. Sorry, I found out by experiment that the stuff won't compile without it. And if I ever knew, I've forgotten. Now, I wrote this note, and I couldn't figure it out how. Static linking preserves it. Yeah, I don't remember why. If you don't compile it with static, it won't work. I no longer remember why. Sorry about that. So you compile it, and then you can run execve, and execve will now create a new $sign. So what this is doing is spawning a different shell. So let's take a look at my options. I have execve.c. That's what we just saw. This will call the execve with these strange parameters correctly set up to execute bin.sh. Now, before we start, let me just say I could run bin.sh. If I ran bin.sh right here, bin/sh, that opens a shell. It's just a different shell. Remember, Unix can use many different shells. In Linux, this is the bash shell, and the bash shell writes your directory here in colors. This is the sh shell, which doesn't. So I'm now in a different shell, and when I exit from that shell, I'm back to bash. So all this code is going to do is what I did there. But it's going to do it from C, and therefore from assembler. So if I run that one, which is execve. I think it's called execve. That does the same thing I did by manually executing bin.sh. So this is the simplest sort of shell. Yes, pointers to pointers, exactly. The structure of this thing can give you a little headache. Shell is an array of 2 pointers, and this is a pointer to the pointer. That's what goes here, a pointer to an array of pointers. And this is a pointer to the text to be executed, and this is the environment. It's a very strange setup. All right, so now if we look at the debugger on this, gdb-q execve, now we can disassemble. Main is the only thing it has. All right. And let me check my point. Around 50, I should see it calling execve. And there it is. Here's the call to execve. So here's where it fills the 3, all the parameters. Here it's putting a 0 on the stack. That's the null. Here it's pushing ECX and EDX. Here's where it's calculating ECX to point to this location, and that's going to be where the /bin/sh is. So this is the point. You see a push, 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 and then a call. This is the structure that calls the execve with the parameters. All right. And that's what you see here. It puts 4. Now here's if you disassemble it, execve itself, that's what does the syscall. So let's do that. Since that called execve, I can disassemble execve. There we are. There we are. And so this moves into parameters A, B, C, and D, these values, and then does a syscall. This is one of the 4 forms of a syscall. Yes, you can. There's an MSF function to look up syscall. That's right. Yes, you can. And we are totally going to do that, not in this class, but later. We're going to use Metasploit Framework to make our shellcode later, and we are going to use those switches to avoid bytes. Yeah, we're not going to write shellcode by hand in this class any more than what we're doing here. The textbook does that, but we don't really need to because we can use Metasploit. Yeah, you got it. Good. All right. So that's what this looks like. It ultimately all goes to a syscall, which is, like I say, all the C libraries just turn into syscalls. They're all just wrappers of syscalls. And so here's more versions of syscalls, the most common being int80 or this call *gs. All right, and so real syscalls will often end up looking like this, being more complicated and have to be rewritten to avoid creating null bytes. It can be quite a chore to write these real shellcodes that do anything valuable in assembler, and we're not going to do any more of it than this because, as a random student is pointing out in the chat, we're going to use Metasploit to make shellcode for us, which makes it much easier. So this is real shellcode that does the execve, and you see it's kind of long, but you can run that, and that will create the execve execution of a shell from inside here. All right, so let's take a look at some cahoots. Let me get them up over here. I guess only one Kahoot today, 127, chapter 3. People knock on MSF, but why read? Oh, that's right. Using MSF to create shellcode and then making your own exploit is only cheating a little bit. Using Metasploit entirely, without even really understanding what it's doing, is what people complain about. Metasploit can make it so easy that you can do an attack without even really knowing what shellcode is. And we're going to do a little better than that. But we are not going to write our own shellcode. We're going to use Metasploit to make the shellcodes. 127, chapter 3. Here we go. All right. The Metasploit is a powerful tool. It just might be so powerful that you don't learn enough about what you're doing. That's all. And there, I think it's more or less on the page. Good. Okay. Right. That might be everyone that's coming. Maybe not. Oh, I guess not. All right, I'll wait a few more seconds. All right. All right. So how do you convert executable code into assembly language? objdump does that. Objdump minus D will show you the assembly language inside the executable program. It will be more precise. It'll take the executable binary code and build assembly language from it to make it more readable. NASM does the opposite. That takes assembly language and turns it into executable code. All right, how do you see all the system calls? That's strace. Good. Popular answer. All right. How do you go from user mode to kernel mode? Syscalls, how you do it. I see a question, how is attendance taken? I don't take attendance. Attending doesn't confer any points. All I know is whether you did the homework and the quizzes. That's what determines your grade. All right. All right, so how do you convert assembly code into object code? Good. That's what NASM does. Assembly code into object code. And object code is code you can execute, although it typically has to be linked first. But it is runnable, executable code. There's another step of linking it, though, before you can actually run it. All right, so what should you do to move EAX0 to use it in shellcode? All right, that's it. The XOR will do the same thing without explicitly referring to the constant 0, which would mess up our shellcode with null bytes. All right, how about move EAX1? What should that be? This is the one that sets the lower 8 bits to 1, and the higher bits seem to be set to 0 anyway. So that's good. All right. All right. All right. All right. So let me stop.